activity is gonna act as your warm-up. We have a flag ceremony held at a 4th of July event. The height of the flag is a function of time. Let me just pause right there for a second. Function of f of x. If you're ever confused about what's necessarily your input or output, whenever it says function of, what follows that is your input. Okay, just a little side note. So time is my input, time is my x. That's why it's on my x-axis. But we have some graphs that are each a possible representation of that function. You had to describe what was going on based on the flag, or based on the graph about the flag. So table 7 for graph A, what must be going on?
The flag would be increasing the height by 1 every 10 minutes.
Okay, so flag increasing, definitely it's going up. And did you say by 1 unit or?
Yeah,
Okay, so increasing by, I think you said, because they also didn't tell us the height. What must the height be? What do you guys think? Do you think that 6 feet, 6 yards? What do you guys think? Okay, so, but yeah, when we do like 1/1, 2/2, 3/3, we could do by 1 unit for, I don't know, each unit of time. But good, I like that we're incorporating the axes, to kind of talk about our rate of change. You could say at a constant rate as well. So flag increasing by 1 unit at a constant rate. What type of graph is flag A? Linear, good. No, oops, that's not what I wanted to do. But yeah, so this is our only, well, not our only one that's linear, but we can expect the average rate of change to be the same throughout. Good. So then table 8, what must be going on with flag B? So it stayed the same height the entire time. All right, it didn't go up or down. It literally stayed the same. It was not moving at all. Is that one linear? Okay, good. It is straight line. Table 1, what about graph C? What must be going on in that one? Okay. Goes up. Stays same. Then up again. All right, and if you really wanted to go a step further, you can say it goes up from 0 to 1, stays the same from 1 to 2, goes up from 2 to, I don't know, 4. All right, table 2, what's going on with graph D? Okay, keeps going up and down. Why they do that, I don't really know, but it looks like that is what's going on. Keeps going up and down. All right, now graph E. Table 3, what's going on with that one, you think? It goes up. And then it stops and continues every measurement. Okay, it goes up, stops, and then repeats. And then table 4, what's going on with graph F? Goes up, and then goes right down. Okay. Good, so we can interpret graphs in context of the real life situation. Now, we're gonna answer which one seemed the most realistic. So, table 5, what did you guys say is the most realistic? So which graph is most realistic? F. Okay, so class, do you agree, is F pretty realistic? Raising a flag at a constant rate, then maybe lowering it, and then leaving it alone? You think that that could be possible? Who said that a different one was the most realistic? I feel like it's kind of an opinion. I mean, there's definitely ones that probably aren't realistic. Josiah? A was the most realistic, and why?
I think you don't believe the private keeps going out there doesn't go back down and stop.
Okay, and again, this is more like an opinion question. We'll read what the book says. Anyone think a different one is more realistic? Personally, I was thinking E. Because like when you're pulling the flag, like you kind of like pull until you can't pull anymore. And then you have to reach up again, pull until you can't pull anymore. So I was thinking more along the lines of E. Which ones are probably like the least realistic? Okay, good. Why would you keep putting it up and down, up and down, up and down? Like that's kind of weird. But yeah. So let's see what the book says about that one, because I feel like that one's more of an opinion, what you think is more realistic or not. So. Assuming that time is measured in seconds and height is in meters, because they didn't specify. You would say that graph E seems to be the most realistic, so what I said. Graphs B and D are the least realistic. Because B, they said they raised the flag, but B shows that they didn't, like they just left it at the same height. Graphs A, C, and F are possible, but unlikely that the flag starts out being on the ground. So you guys see that those flags, A, C, and F, start at the origin, which like when you're raising a flag for an event, we usually don't keep the flag on the ground to begin with, okay? Questions on that? All right, so good little exercise to practice interpreting graphs. We're gonna do a little bit more with that in a second. Today we are knocking out graphs 8 and 9, which are about interpreting graphs and comparing graphs, which we've already kind of done a lot. So that's why I combined them so we have more time to review the test. But the goal of today is to compare the graphs to learn about the situations they represent, be able to explain average rate of change in terms of what's going on in the situation. On a side note, what's the formula for average rate of change? We learned it yesterday. Okay, good, thank you. Remember, I'm not providing that for you. You've got to memorize it. But it's really similar to a formula we've already looked at before, slope, but now we use this for all functions. Not all functions are going to be straight lines. So still similar, but for average rate of change, you'd have to specify from what intervals you're looking at. Because if I look back at our flags, the average rate of change from here to here on flag C is going to be different from here to here. So we would have to specify what interval you're looking at. So that's going to be the case moving forward. All right, but back to the objective. You got to be able to compare features of graphs and functions and explain what they mean. Make sense of graphs in the form f of x equals g of x, and know how to find solution. So I'm recording right now. I always record FYI. So if you're ever not here, thank you. If you're ever not here, make sure you're keeping up with the class. There's no excuse. Puzzle piece is actually two puzzle pieces. I forgot to put a little screenshot, but they're there. All of homework assignments, aside from maybe the puzzle piece study guide, is posted for the rest of the semester. So please feel free to get ahead. A lot of it you might already know how to do. And then here's all the assessments for the rest of the semester, including this week. We only have 3 weeks. So any questions? All right, let's end this last unit strong. So far, everyone's been telling me it's easy. So let's continue that. Stay dedicated to the unit we're currently on. All right, so still about the flag raising. Here's another graph that relates to time and height. Can this graph represent the time and height of the flag? Explain the reasoning. And then also, is this graph a function? So now answer these 2 questions. Feel free to discuss with your group. The reporter will switch, so, or might not, depending on what the criteria is next, but this is your point of discussion. Could this represent the situation, and is it a function? Safe? Yes. Graph represents the time and height of the flag. Okay, so they say no. Class, you agree with no?
Yes.
Okay, so, and they said because, again, sorry, can you say it a little bit louder? That it was put up, taken back down, all within the 3-second interval. Does anyone have a different way of explaining why that is not the correct flag? All right, what about, where's like the initial height? If time is supposed to start at 0 seconds, then where is like, what's going on with the interval from like 1 leading up to 3 and then after? So even if it's, I mean, they said it could be that they put it up and took it back down all within 1 time frame. But does that seem really realistic? Probably not. So here's what else you probably could have said that the book says. They have a few responses. So assuming time is seconds and that height is meters, this graph shows that the flag, table 8. This graph shows that the flag being at all heights between 0 and 6 meters at 3 seconds of time, which is impossible. Yeah, you can't be at all heights within 1 second. And then it is not a graph of a, oh, just let me hold off on that part. I'm going ahead. Okay, so no, and you could have said for a lot of reasons. But it just really doesn't make sense. All right, now whoever spoke last for your group, go like 2 to the left. Whoever spoke last for your group, go 2 to the left. So table 7. Is this graph a function, yes or no? And why is it not a function? Okay, good, they said it beautifully. So X is just 3, but it has many different Y's. All right, remember what makes something not a function? Are X's that repeat with different Y's. So now let me have you look at this really quickly. Like go back to the first 6 flags that I asked you to look at. See if any of these are not functions. So we already decided the one that's just a vertical line is not a function. Now decide if any of the others are. Give you like 30 seconds. Josiah. Yes. Table 8, do you think that any of these are not functions? And if so, which ones? Okay, so they think that they're all functions. Anyone disagree with that? Okay, good, they are correct. The first six are all functions. Now, I'm gonna introduce you to something that maybe you should jot down where there's free space. But when you have graphs, because I mean, we've looked at functions when they're tables, when they're coordinates, like you really just gotta look at those numbers and that things. But when it's graphs, you might be better off using something called the vertical line test. In this test, it's to see if something's a function or not. You basically draw a vertical line through your graph. And if it touches any of the vertical lines on more than one spot, then it's not a function. So that's another reason why this one is not a function. This fails the vertical line test because I could draw a vertical line through where x is 3 and we have all those different y's. But it really just has to fail once for it to not be a function. So we could put that this one fails vertical line test here. So that's definitely why it's not a function, because it touches all over that line. But say I had graphs that looked like this, or like that, or we can even copy one of the ones from earlier. If I were to draw vertical lines through this one, would this be a function? No, it fails here, here, and about probably a bunch of other places, but it only has to fail once for it to not be a function. So this makes it not a function. Would this one pass the vertical line test, do you think? All right, so let's try that. Draw a vertical line. And at any point, does it touch more than once on the same vertical line? So this one passes. So this one is a function. And then one more down here when you extend the page. If I were to try the vertical line test on this one, does this one pass the vertical line test? Yeah. So this one is or is not a function. Okay, so now that's a quick way to tell if you have graphs. You can also do it from discrete graphs. So discrete graphs would be like the dots. So say I had something that looked like this. Would this pass the vertical line test? All right, looks like here is where it would fail, right? So it fails, therefore it's not a function. So that would say that you have an X with more than one output. Still just either way be able to tell if it's not a function or not. Okay, so good, questions on that? All right, we are moving on then. So now we're gonna look more at the comparison of graphs. So this is more your lesson 9 stuff. So on the back, we have wired or wireless. H of T is the percentage of homes in the United States that have a landline phone in year T. C of T is the percentage of homes with only a cell phone. Here are the graphs of H and C. First, you are going to estimate H of 2006 and C of 2006 and explain what each value tells us about the clock. We've done that before, so I'm not super concerned about that. Kind of review. And then what is the approximate solution to C of T equals 20? And then explain what the solution means in that situation. I'll give you about 3 minutes. See what H of 2006 is about. Or can you tell me which line should I be looking at? the landline phone. Okay, so feel free to reread the description if you're ever unsure. Sometimes they use random letters. All right, but H of T is the percentage of homes in the United States that have a landline phone. So you should be looking at the blue line for the answer of what H of 2006 is. Table 2, can you tell me what the value is? Approximately. Okay, maybe 83, maybe 85. But something close to that, you have to approximate it. They're counting by 20, so like here'd be the halfway mark. Definitely between like 80 and 90. Probably closer to 80. All right, now that's what we're estimating. Now, what does that mean? Table 3, can you tell me what it means? Okay, perfect. So 83% of people had a landline in 2006. So like house phones. Right, perfect. Where am I? Table 4. So what's the value of C of 2006? Yes. Okay, about 18, I'd agree. Maybe 15, I don't know, but we're having to approximate it, so our answers might be slightly different. But yeah, close to 20, maybe a little ways, but 18, you're having to approximate it. Now, what does that mean? 18 what, class? Perfect. If you heard that. So 18% of people had cell phones in 2006. And I use the little quotations to show of people had, so that way I don't have to rewrite it again. Now the approximate solution to C of T equals 20. Table 5, what'd you get for that? Okay, so notice in this one class, they did not give us an input, and I know they didn't give us an input because inputs go in the parentheses, right? It's usually F of X. But they did give us a value, so that value that they gave us must be an output. So in that case, make sure you're looking at function C, that's the cell phone one, so look at the red line. Find where the output is 20, see where it hits on the line. I would agree, that's 2008. Now, what does it mean? Well, in the year 2008, what happened? Okay, good. In 2008, 20% of people had cell phones. Home. All right, I know it's cell phones, not landlines, because they use the C, which they said is for the function where people only had cell phones. Okay, so questions on that. We're gonna add the additional 2 questions now. All right, so let me make this a little bit bigger. So now we're on questions 3 and 4. Determine if each equation is true and be prepared to explain how you know. So I've not shown you stuff in this format yet, so let's maybe do A together. So we have C of 2011 is equal to H of 2011. So what are they giving us? What's this 2011, an input or an output? So I need to look on where my inputs go. At 2011, which would be here. Now I have landlines up there, cell phones down here. We could put the values there if you want. What's approximately C of 2011? So maybe 30, maybe 31, depending on how you approximate it. What's approximately the value of H of 2011? Probably say closer to 70, but sure. Okay. Are these equal? So then this is false. If they were equal, what would the graph look like? They would intersect, just like our systems, if you remember that. If they were equal to each other, they intersected. So now look at B, and I'm not gonna give you a whole lot of time, just look at it, think about it, don't say it out loud yet. But look at B, where C of 2015 is equal to H of 2015. Think about it yourself, is that true? All right, so raise your hand if you think that that is true. Okay, good, because that is correct. So you could say true, and you could actually put the values of the outputs, or you could say true because they intersect. So they have the exact same coordinates where they intersect. Now, questions on that, by the way? Now for number 4, between 2004 and 2015, did the percentage of homes with landlines decrease at the same rate at which the percentage of cell phones to only homes, I don't even know what they're saying, increased? Sorry, reread that yourself. I kind of messed it up. Explain or show your reasoning. Did the percentage of homes with landlines decrease at the same rate at which the percentage of cell phones only increased? Explain or show your reasoning. So if this were like a constructed response question, you could talk about the graph and maybe be right. You can support your answer with calculations. But are the average rates of change about the same? Okay, so Tristan, what did you say for number 4? Did the percentage of homes with landlines decrease at the same rate at which the percentage of cell phone only homes increased? Okay, so intersecting would only help if they intersected like at the middle. That would only help answer this one if they intersected like at the middle of where they started. So like at 2004, one is here and one is here. So would you say that they intersected like at about the halfway point of that? Okay, so in that case, then that could support it. Parker, did you say something different? Okay. So to answer this, let me show you what the book said, because the book could actually support either way. But the only way to really say is with mathematical calculations. So I'll show you. And there's times like that where like on the constructed response test, I sometimes give points if you said yes or no, but your justification was good. So just depends on what you said. So here's what the teacher guide says. Yes, one decreased at roughly the same rate as the other one increased, so just visually. And then someone else said, no, the percentage increased at a rate close to that by which the percentage of the other decreased and not exactly the same. So to really support your answer, like on your state testing, you get more points if you include the calculations and things like that to support your answer. They did the math for the cell phone only homes. What did they do right here? What's that called when it looks like that? That's my average rate of change. They calculated the average rate of change for the 2 points. And of course, they have to estimate the outputs. So, you know, it could be slightly different based on what you estimated. And then they did the same for the average rate of change for the home landline people. Okay, and when they calculated it, the cell phones increased by about 3.8% each year. And the landlines decreased by about 4% each year. Wouldn't you say that that's about the same? Is it exactly the same? No. That's why you could have said yes or no, but just be able to support it. So yeah, it's about the same if you run. Questions on that one? Okay, I know it's been a long day, but let's knock out this last one and then you'll have time for your practice. So together. And we'll just rotate through the table so that it's quicker. So table 8 is F of 2 or G of 2 greater? Okay, G of 2, class, agree, disagree? So look at where the input is 2. G is the line, it's higher than where it hits for the F. So yes, that's true. Table 1 is F of 4 or G of 4 greater? They are the same. So look at where the input's 4. See where that touches on the graph. Sorry, my pen is taking the worst time to stop working. Okay, there it goes. Okay, but here it is. They are equal there. So neither of them are greater. Table 2 for F of 6 or G of 6, which is greater? F of 6, I would agree. The U-shaped graph is higher than the line, so F of 6 is greater. Table 3, F of 8 or G of 8? All right, so now you can do it from a graph. Is there a value of x at which the equation F of x equals G of x, class? What would the x value be? And then are there any others?
Yes.
What is the other? Okay, yes, there's 2 areas. That's where they intersect. Where x equals 4 and x equals 9. They have the same values at those areas because they intersect. All right, and that's really all. Questions, comments, concerns? All right, so now you have some time to do your practice. The practices are usually short, so you can knock out at least a few of them. Yeah, sorry. Were you able to finish or?